Hey, Ashley is with us. Good deal. Let's see who else we've got here. Ashley, it's just you and me. That's it. The others haven't showed up yet. Oh, no, wait, there's Ryan. Ryan is with us. So we've got a class. That's good. Class starts in about 3 minutes. Do you have any questions for me?
I don't see homework 24 on Blackboard.
Let me look and see here. Thank you for asking. This is 24. Maybe I need to check that. Maybe it didn't get on Blackboard. But this says 1778. And it's due tomorrow, theoretically, unless I've fouled up. Let me see what that is. I'm curious. 1778. $17.78. Okay, yeah, that's a really nice problem. It's a pulley with two masses. I'll check on it and see if I fouled up, but go ahead and do that. But if I didn't put it on there, you'll have a hard time submitting it, won't you, Ashley? Oh, well, we'll work it out somehow. Now, the homework for today is 1796. And it's on page 464. It's due Saturday. Theoretically, this is due tomorrow. But I'll check on it. I'll get my IT person to look at it. And your exam should be available today. It should be available to you, and it's due Saturday at midnight on chapter 16 and 17. Today's the last day for chapter 17. I'm going to try to get into chapter 18 just a little bit here today, but chapter 18 is not on your test. Okay, that was a good comment. Anybody else have a question or comment for me? Let's see if we've got any more customers here. Oh, yeah, Mark is with us too. Good going, Mark. So, class is starting. It's 9:30. According to my watch. Let me see what my cell phone says. My cell phone says there's an Amber Alert. Boy, that's scary. Yeah, it says 9:31. Class has started. Okay, do anyone have any comments or questions before I get to talk about what I want to talk about?
I got one. This
Yeah,
is Braxton.
yeah, hey, Braxton.
I don't see homework. Oh no, never mind. I see homework 24 now. Never mind.
Is it on Blackboard?
Yeah, it's on there.
Good.
I didn't see it yesterday, so yeah.
But it's on there. Okay.
Mm-hmm.
Okay, well, here, let's start things off. Now,
What you told me? I'm not this rowdy rebel figure like you.
there, I muted you, but anybody that wants to talk to me can unmute and say what they want. First thing, let's have a little tiny review. I want you to see if you can write the different versions of Newton's second law. Newton's second law. There's actually four versions that I've taught you guys, and it is in your book. I'm going to shut up for a tiny minute, and we're having a review here of well, that's what this chapter is all about, you know. Chapter, what are we doing? 17? Yeah. Chapter 17 is all about Newton's second law. In fact, this whole course centers around Newton's second law. If I can get you to understand Newton's second law to the point where you could actually use it and apply it, I will not be a total failure. And I don't want to be a total failure. I want you guys to go on and do good and get your degrees and be very successful. That'd please me. Okay, I'm going to shut up. You got an opportunity now. See if you can write those four. See if you can do it without peeking at your notes or your book. But if you have to, go ahead and peek. It's okay. I'll be quiet for I don't know, a minute and a half or so. If you really know those, it won't take you very long to write them. Go for it. I bet you got the first one here. I'll write it, and I hope that you have this one done. There's the first one. I hope you all got that one. But there's three more. Go ahead. Well, here, I'll write another one. How about this one? Did you get this one? Ta-da, and did you get that one? I hope so. But there's two more. We're having a review right now. And I've asked the class to write the 4 different versions of Newton's second law. Well, there's 2 of them, but there's 2 more, and here's how they go. Now the book writes it like this. Let's see if I can find it here. I write it a little different than the book does. The book writes it like this. They use a point P rather than A, but that's just a dummy variable. This is their secret symbol for the sum of the kinetic moments. But the way I write this is like this. And see, these things are called kinetic moments. They say just the sum of the moments about some point other than the center of gravity is the sum of the kinetic moments. Well, those are kinetic moments, but there's a 4th version that goes like this. And again, these are kinetic moments. And this equation here has a spin-off, a simplification equation that you can use if you have a fixed pivot. And I'll show you where that is in the book. By the way, I just saw this equation. It's in your book on page. It's on page 456. And this equation that I'm going to show you now, if I can find it here. There it is. Yeah. See, if you have a fixed pivot, this term here drops out because there's no horizontal acceleration of a fixed pivot pin. It doesn't have any acceleration. It's a fixed pivot. It just sits there, maybe twists, but it doesn't go anyplace. It can't have acceleration. If this term drops out, you can write that equation like this. And they have that equation on page 442. Only they have an O there. It's just a dummy variable. It can be any point, A, B, C, D, E. They have O. It's some point other than your center mass. And the beauty is you can use this equation here also if you have a ICZV. Let me see if I can find that. I just saw it. If you have an ICZ, there it is. There's a little room right here. If you can find your ICZV, and I've shown you how to find that. We've done that. Then the sum of the moments about they just go IC. They were too lazy to write ZV equals the moment of inertia about IC. They were too lazy to write ICZV. And so again, this term here drops out if you have, if this point A is your instantaneous center of zero velocity. And you'll find this equation on page 456. Yeah, it's on the same page as this one here. Well, there's your review discussing Newton's second law. Did you know that there are 4 versions of Newton's second law? If you ask for Newton's second law, you gotta give all of those. It's not just this first one. That first one is for translation. What if a body is rotating? Well, then you have to use one of these. Now, you don't have to use all of them. In fact, these first 2 is all you need. It's just that these other 2 make it a whole lot easier to work problems. But you don't really need them. They just make it easier. Is there any question about our quick review of Newton's second law? Here's your chance to ask me something if you want. Well, I guess there's no question. Let me see who's on board here. Oh, we got a big class. We have Mark, Braxton, Ashley, Ryan. Let's see, Tyler, Taylor, Shane. We've got a good class. Any questions or comments on our little short Newton's second law review there? All right. Well, if you're happy, I'm happy. Let's use them. Let's just go through and do all of those. Wouldn't that be good? And here's your homework. And according to the Blackboard, this is due tomorrow. This is due Saturday, and you have an exam. It's a take-home online exam, and it's due Saturday over chapter 16 and 17. Okay, I'm going to erase all this. Say goodbye to all this wonderful stuff, unless you have a question. All right. Let's get rid of all that and let's do a problem. Here we go. Okay, now this is problem 17105. 17105. It's on page 465. Page 465. And you know the drill. You're supposed to draw 2 free body diagrams. So here goes. I'm going to do that. Here's the first free body diagram. We'll put another one over here. Oops. Okay, this this is going to be a 30-degree angle, which sort of like that. Oops. Here we go. And I'll put one here, same way here. And there's a 30-degree angle here. 30 degrees. Okay, this is 1.5 foot. 1.5 feet radius. And they said the coefficient of static friction of the 50-pound roller, it's a 50-pound roller. Static friction is 0.25. Let me write that down. See, here's the ground. Here's the ground. And we have static coefficient of friction 0.25. Find the maximum force P that can be applied to the handle so that the roller rolls on the ground without slipping. Find the angular acceleration of the roller. Assume the roller to be a uniform cylinder. Okay. Well, now our first job is to get our red pencil or a red pen out and put the red stuff on both of these diagrams. Remember on those 4 Newton's second law equations, there was equal sign, and there were some terms on the left side of the equal sign, and there were some terms on the right-hand side of the equal sign in Newton's second law. Like on the first one, for instance, the sum of the forces on that first one was MA. See, there's stuff on the left-hand side. Well, see, this diagram here is for the left-hand side of Newton's second law, and this diagram here is for the right-hand side of Newton's second law. Only there's 4 equations. You don't need all of them, but here, let's do this one too. Sum of the moments about G is equal to IG alpha. See, that's the right-hand side of Newton's second law, and this is the right-hand free body diagram. Now I want you to take your red pen or pencil. If you don't have red, it's not the end of the world. Take whatever you got there, pretend it's red, and put in the red stuff. I'm going to shut up now for a minute, and let's see if you can put in all of the forces. See, these are the actual forces. These are the actual moments. These are called kinetic forces, and these are called kinetic moments. Get your pretend red pencil out and put them in. I'll shut up for a tiny bit. Go for it. Now, what we're doing right now, if you tuned in late, we've drawn our 2 free body diagrams for problem 17-105 on page 465. And right now, we're putting in the red stuff. Go ahead. Well, you ought to be done by now. Let's go ahead and put the red stuff in. Now, they said there was a force here, and I'm going to put it in red, and they called it P. I guess you could call it whatever you wanted, but I think they called it P. Yeah. And then you'll have a normal force here. I usually call that eta. It's a Greek letter, eta, ETA, alpha, beta, gamma, delta, alpha, beta, gamma, delta, zeta, eta, alpha, beta, gamma, delta, zeta, eta. It's, you know what? It's the 6th letter of the Greek alphabet. And then you have a weight. You have a weight of 50 pounds. 50 pounds. It doesn't show up very good. Let me write it a little darker maybe. You have a weight of 50 pounds. Now this normal here is going to be bigger than 50 pounds. I probably should draw it a little bigger. There. The reason why it's going to be a little bigger is you have two forces pushing down. So you got 50 pushing down, and this external force P has a downward component. They're going to add up. And so that normal is going to be bigger than 50. If it weren't for P, if there was no P, then the normal would be 50. But you do have that extra force pushing down. That makes the normal bigger, doesn't it? And then you have friction. Don't know where to put that. We'll just put it's either going to the left or to the right. Let's ask some of our excellent students. We've got some wonderful students here. Tyler, unmute and say hello to me, please, Tyler. Earth calling.
Hello.
Yeah, hey, Tyler. Hey, Tyler, you got a 50-50 chance on this. That friction's either going to the left or it's going to the right. What do you think?
Is it the left?
Okay, now Tyler has, we'll ask a couple other students here. Tyler says the friction's going to the left. Let me go with my friend Shane. Shane, unmute and say hello to me, Shane. Please.
Hello.
Hey, Shane, you get to vote on this. There's a friction force here. It's either going to the left or to the right. What do you think it's doing? You got a 50-50?
The right.
Shane is going to go to the right. Let's take one more student here. How about my friend Mark? Mark, unmute and say hello to me, please, Mark.
Hello.
Mark, you got a 50-50 chance now of getting this right. What do you think? The friction's going to the left or to the right?
Let's say to the left.
Mark says to the left, and it would be fun to get all the others. Here's the interesting thing: it can't be both. It's either one or the other, and one of them is right, and the other one is wrong. But how do you figure it? Well, here, let me help you. We'll come back to that. Let's get the red stuff on this one now. Now on this one, these are called kinetic forces and kinetic moments. And here's what I hope you have for your MA. There it is. That's called a kinetic force. It's going to the right. Now you look at your drawing that you've done. How'd you do? Did you get that? I hope so. But see, there's also an I alpha. I think that this roller is going to turn clockwise, and I think your I alpha is going clockwise. So I just completed the what they call kinetic moments and the kinetic forces diagram. But let's solve this business about the friction, shall we? Now here's the dirty little secret of figuring which way that friction's going. Suppose this surface was really slick, like ice maybe. I don't know if you've been ice skating, but that ice is very, very slick, isn't it? And if you had a very, very slick surface here, I don't think this roller would rotate at all, because see, these other forces, this normal and this weight and this force P here, they all go through the center. They don't give you any twist. We know it's going to twist clockwise. See it? To twist clockwise, can you see that the friction's got to go to the left? And so Tyler, yay, we'll put a happy face for Tyler and a happy face for Mark and an unhappy face for Shane and all the rest of you that thought it was going to the right. Did you understand that? The secret is pretend the friction has been reduced down to practically zero. What would happen? Well, it would just slide. It wouldn't rotate at all if there was no friction. But we know it's rotating clockwise, so the friction's got to go to the left. Any questions on that? Okay, well, great. We got our diagrams done. Now let's go ahead and get the moment of inertia. Now for a disk, they said we could treat it like a cylinder. If you look in the flap of your book, it says 1/2 mr squared. Let me see if I can find that. For a cylinder, it's the back flap of your book. It says here 1/2 mr squared. I'm looking at it. That's it. Okay, well, let's do it. Now that's the moment of inertia, the mass moment of inertia about the center of mass. And it's equal to 1/2. But you don't go 50 pounds. You have to go slugs. Do I need to explain slugs? Times 1.5 feet squared. All right, do that with me. I'm going to do it, and I'm going to get the moment of inertia. You do it. Go for it. Well, I got an answer. I'm getting the mass moment of inertia about the center of mass to be 1.74689 blah, 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 slug feet squared. Now, if that's wrong, you speak up. But I think I probably did that right. And let's call this point A. We might need the moment of inertia about point A. So why don't we get that? Now to get that, you have to use this equation here. This equation has a name. See, that distance there is the distance between A and G. That equation has a name. Let me ask one of my excellent students the name of that. Taylor. Taylor, unmute and say hello to me, please, Taylor. Earth calling Taylor. Earth calling Taylor. Come in, Taylor. Uh-oh. Coffee break. Well, let's try another friend here. Ashley. I can count on Ashley. Ashley, what's the name of this equation?
Parallel axis theorem.
He's got it. It's the parallel axis theorem. Good going, Ashley. Well, let's do it. You know what IG is. We just did it, and you know the mass, and you know that distance. Go ahead. I'm going to do it. You do it. Let's get our moment of inertia about A. Go for it. I got an answer. I wonder if anybody's getting 5.240 blah, blah, blah. Let me just round it off because I'm running out of room here. Slug. Oh, gee, I'm running out of room. Slug feet squared. If you got 5.2407 slug feet squared, say uh-huh. See, I could be wrong. That's why we're doing this. Was that an uh-huh?
Yeah, I got the same answer.
Yeah, there's one. Give me another uh-huh out there.
Uh-huh.
Yeah, I bet that's right. Okay, well let's continue on with our problem. Now they want to know a bunch of stuff. Let me see what we're supposed to find out. Let me read this. It says here, we're doing problem 17105 if you just woke up from a daydream. And we're supposed to find the maximum force that you can apply so that the roller doesn't start slipping. See, if you make that force too big, it'll start. Actually, I think they used the wrong term. I think it'll start sliding. I don't think it'll start slipping. They're playing a little bit loose with the English language there. But see, if you make that too big, it starts sliding along. Kind of like it would if you had a real slick surface, like an ice skating rink. You don't need to make it that force very big for it to slide along on the ice skating rink. But what I think they mean is sliding, not slipping. See, slipping is when this thing has got a motor maybe, and it's spinning and it's slipping, kind of like you do when you put on your accelerator and you're slinging mud out behind your tires that's connected to the motor. They call that slipping. See, sliding is when you put on your brakes and you just slide. You put on your brakes and you slide. But we'll forgive them for that. But now, how do you go about that? Well, we need to talk to you about what they call impending motion. See, the way friction works is static friction. Here's the equation. It's really an inequality. Static friction is equal to the coefficient of static friction. It's equal or less than the coefficient of static friction times the normal. That's what you have with static friction. Now there's a thing called impending motion. I don't know if anybody's ever taught you this. impending motion. What that is when your static friction is precisely equal to your coefficient of static friction times the normal. And see, what happens is, if you try, you can't make the static friction any bigger than that. That's the maximum. Another way of writing this would be to say the maximum friction instead of impending motion. The way I demonstrate this to my class when we can meet in person is I'll grab a chair and I'll gently start pushing on it, but it doesn't go anyplace yet because I'm not pushing hard enough. So I push a little harder. I'll push hard enough to where I can get kind of a crease in my hands from the chair that I'm pushing on, and it's still not quite ready to move. But if I increase the force on that chair just enough, I reach what they call impending motion, and the chair breaks loose. It breaks loose and it starts to move. At that point, you've reached the maximum static friction. Before it was less than this, but now it's equal to that, if that makes any sense. So we have a nice equation there for our friction. It's going to the left, and it's equal to 0.25 times the normal. So let's write some equations and see if we can solve them. Here we go. Any questions so far? All right. Well, I need some room here. We want to keep that. That's important. We probably want to keep that. That's important. All right. Well, how about this? The sum of the forces in the y direction, and we'll just say y is going up, okay? And we can have x going to the right, as usual. The sum of the forces in the y direction are, we have our normal going up, minus our 50 pounds, going down, minus a component of this force. We don't know what that force is, but we know the angle is 30 degrees. And that component would be P sine of 30 degrees. If you don't know how to take components, I'll explain that. You just have to ask. Just say, Mr. Griffin, show us how to get that component. Nobody asked, so I think you know how to do it. You know how to get the component. See, that's the component going down. This has a component going to the right. It has a component going down. The component going down is P sine 30. Well, that's it, guys. And in the y direction, you get 0, because this thing does not accelerate in the y. So we have one equation there. Unfortunately, we have two unknowns. We don't know eta and we don't know p. But we're not done yet. Let's do the sum of the forces in the x direction. Let's see what we got there. In the x direction, we have, well, you have the component of p going to the right. You have p cosine of 30 degrees going to the right, a minus the friction. Now you could write the friction as 0.25 times the normal. That's it. Now this is not equal to 0 because it's accelerating to the right, and it's equal to ma. It's equal to the mass in slugs. That's in slugs times the acceleration. Okay, well, great. Well, there's those two. Now let's write the this equation here. The sum of the moments about the center of mass. We're going to write that equation. Well, the normal and the 50-pound, and you know what? All three of those red forces go through the center. They don't give you a moment about G, do they? The only one that does is this friction, and it's equal to the friction times 1.5 feet. Friction's 0.25 times the normal, multiplied by 1.5 feet. That's it. It's clockwise. We'll write this clockwise. We'll write all these terms clockwise on this equation. And on the right, we have IG alpha. Well, there's IG. It's 1.74 blah, blah, blah. Slug feet squared alpha. Okay, well, great. I need the room. I'm going to erase it. I've got my moment of inertia right there, 1.74689. I don't need this one anymore. Well, we've got a couple equations now. Can we solve it? Let's see. This equation here, I'll box it up for you. No, wait a minute. We have three equations, don't we? Here, let me box these equations up. We got this equation here. It's a nice equation. And it has two unknowns. It's got eta and p. Now this equation here, it's got eta and p, but unfortunately, it has another unknown. This equation has p, it has eta, but it also has a. So if we had two equations and two unknowns, we could solve this, but we don't. But let's look at this equation here. Now this equation, let me box it up for you. We'll put a little box around it so it'll just stand out where we can see it nice. You know what? We have three equations, don't we? Let's count the unknowns. Here, let me write that down. We have three equations. Now let's count the unknowns. Well, let's see. We have eta and p and a and alpha. Holy cow, there's four unknowns. Oh me, oh my. Here, I'll write them for you. There's p, there's eta, there's a, and there's alpha. We have three equations, but we have four unknowns. Anybody have any help? Can you help? Help. What do we do now? Can somebody help me? We got three equations, but there's four unknowns. What can we do? I bet you know. Let me go to one of my wonderful students here. Ryan, unmute and say hello to me, please, Ryan.
Hello.
Ryan, we got three equations and four unknowns. What should we do?
Can you replace the A in equation 2 with R alpha?
Beautiful. That's it. Wonderful. Excellent. That's the secret. See, A is equal to R alpha. And we know R, it's 1.5 feet. 1.5 feet times alpha. You could do like Ryan said, we could replace it in here. That's a great idea. Or you could just leave it like that. You got four equations and four unknowns. We just need to do some algebra. Now, we're going to do the algebra now. But I like Ryan's idea. I like replacing this with 1.5 alpha. Okay. Let me set up a 3x3 simultaneous linear equation. Doesn't that sound like fun? It sounds like fun. Hey, we never used the other. We've got 2 more equations that we never used. But I think we could solve it with this, don't you? I don't know. Let's write these other equations and see if that'll help us any. Especially this one here. The sum of the moments about A. We haven't done that equation yet. That's equal to IA alpha in this case because it's rolling. It's still rolling. It's on the verge of slipping, not sliding, but slipping. And if you wrote this equation, what you'd have is the sum of the moments about A. Well, you'd have to, this is the only force that gives you a moment about A, and it's P, we don't know what P is. It's acting at a distance of 1.5 feet. And what you have to do here is you have to take the angle between this R and the P, and it looks like the sign of either 120 or 60, it's the same. I think I'm just going to go sine of 60. And if you don't understand that, I'll come back and talk about that. But see, that's it. That's the only moment acting about point P. See, the friction goes through P, the normal goes through P, the weight goes through P, but this one doesn't. It gives you a clockwise moment, P times 1.5 foot times the sine of 60. See, there's a 60-degree angle right here. See it? There's 60 degrees. And that's going to equal I of A times alpha. Well, I of A is the 5.2407 slug feet squared times alpha. So let's see what we've got now. We've got another equation here. Let's box that one up. I kind of like it. Now this equation has P and alpha in it. It's got P and alpha in it. Now we have basically 4 equations. You could combine that one in there. We've got an algebra problem to do, don't we? Okay. Well, it's a little bit ugly. Teeny tiny bit ugly, guys, but I think we did everything right so far. Let me see how I did this. Okay, I've got this equation here. I kept that one. And I have this equation here. Let me put a little star by these. These are the equations that I wrote down when I did this before. And then I have this equation here. Yeah, I've got that equation. I just wrote out those 3 equations is what I did. I think there's room here. Now let me make some room and we'll do that. Okay, we're going to make some room here and do that. You see that minus P sine 30? That's minus 0.5 P. And you see that plus eta equals 50. Can you get from this first equation to that? I bet you can. Okay. Yeah. And then what I did was I did, okay, I'm getting mixed up now, just a minute. I got lost here. Yeah, that one I understand. I don't know what I did with these others. Oh yeah, here we go. I think I broke this into 3 unknowns. I think what I did was I did this. A minus 0.5p plus 0 alpha. See, this equation doesn't have any alpha at all. Plus 1 eta equals 0. Yeah, see there's 1 eta. Yeah, that equation is good. I took that equation and I just rewrote it. Okay, that's good. And then I took, I wonder where I got this equation from. See if you can figure out what on earth I did here. 1.299p minus 5.2407 alpha plus 0 eta equals 0. Now, where on earth did I get that? Don't know. Well, the cosine of I don't know where I got that equation. This one has a 0 eta. It can't be this equation. This one has an eta. Maybe I use this one. This one doesn't have. I bet this is it. I bet if you take, yeah, that's what this one is. I don't think I did that one yet. If you take sine of 60 times 1.5, I think you'll get a 1.299p minus the 5.2407 alpha. There isn't any eta, and it's equal to 0. Okay, now this equation here, I just rewrote it there, and this equation here, there it is there. And then I have a third equation that goes like this, 0.86603p minus 2.3292 alpha minus 0.25 eta equal, just a minute now, this is a screw up. This is equal to 50, not 0. See, that 50 goes over on the right. That's equal to a 50 over on the right. There you go. That equation is correct. This equation comes from here. Wait a minute. This equation comes from here. Yeah. Now, where did this equation come from? Good question. Don't know. It's equal to 0. But where did it come from? I bet it came from here. Look, there's a minus 0.25 eta, and cosine of 30 is 0.866 p minus 0.25 eta, and then if you'll take this a here, like one of my excellent students said, and write that as 1.5 alpha, you'll get 2.329. You'll get a negative when you move it over. So this equation here, I'll tell you where I got that from. I got it from here. I never did use this equation here, did I? I could have. I think we have more equations than we need, but we have 3 equations and 3 unknowns. And what I did was I put those into my my simultaneous linear equations calculator. See those 3 equations there? There they are. Do you have a calculator that does 3 simultaneous linear equations? I bet you do. I'm going to turn mine on now. And I'm going to push the button that says simultaneous linear equations. Then they want to know how many equations. Well, there's 3, so I pushed in a 3. And now they want me to put in the numbers. So I'm going to put in minus 0.5, 0, 1, and 50. I'm putting in these coefficients. And then they want these coefficients here. Here they go. 1.299, negative 5.2407, 0, 0. And now these coefficients here, I'm plugging them in. 0.86603, negative 2.3292, and negative 0.25, and 0. And then I push the magic button, and it gives me the answers. Here we go. It says solve, so I'm going to push it. And it says, I'll make some room down here. It says P is equal to 76.36 pounds. And alpha is equal to 18.93 radians per second squared. And eta is equal to 88.18 pounds. Do you have a calculator that can do that? And let's see how we're doing, and then let's work the let's work all of Newton's second law equations on this. That'd be fun. Go to the back and look up the answers to 17105. It says back here 17105. Alpha is 18.9. Hey, we did good. We got 18.93. They rounded off. They said P is 76.4. We got 76.36. They rounded off. Hey, we got the same answers the book got. Wow. So we're in agreement with the book. Now, we never did get the linear acceleration. Let's do that. Well, to get that, you just go 1.5 foot times alpha. So let's do it. We know alpha right here. So take that 18.93 times 1.5. And I'm getting 28.395. You could be lazy and call it 28.4 feet per second squared. Ta-da! And we got our linear acceleration. Did we ever get the friction? Well, the friction is going to be the maximum friction. We never did get it, but let's get it. Remember, the friction is what they call impending friction. It's the biggest friction you can get. It's equal to 0.25 times your normal. Isn't that what they said, 0.25? Yeah, we can do that. There's your normal. Take 88.18, multiply by 0.25. And so the friction is 22 here I'll round it off, 2205 pounds. Yay, we got the friction, we got the linear acceleration, we got the angular acceleration, we got the normal, we got that external force. The only thing we haven't done is we haven't checked our work with those other Newton's second laws. I think we should. But before we do that, we're going to check our work here in just a minute. It's called checking your work. Now, you could have done this without using one of those fancy simultaneous linear equations calculators, just by doing algebra. But I was lazy, so I wrote it out as a 3 by 3. See it? Three unknown simultaneous linear equations. There they are. They all came from here. Before we check our work, is there any question from anyone on what we did? I got a bad feeling about this. Maybe some of you got lost. I'm hoping not, but anybody want to express any comment so far? Okay, well, we're going to do a Newton's second law check on this. Now we've already done another version of Newton's second law. We did this one here. The sum of the moments about A equals IA alpha. That's right here. There it is. We already did that. We did this one too. The sum of the moments about G. That's, let's see if I can find where the heck that is. Some of the moments about G. You know what? That's this one, isn't it? Some of the moments about G. What's this 1.7 thing? I got lost there. Where did this equation come from? 0.25 eta. Well, that's friction times 1.5. That's the moment due to friction about G, and it's the only moment about G. See, here's G right here. And so this is the sum of the moments about G. And so that's the, I know what that is. That's the moment of inertia about G. This 5 point something, that's the moment of inertia about A. But this 1.7 something, that's the moment of inertia about G. Okay, but we've already done that one, and we've done that one, we've done that one, but there's one more, and this is going to be our check. There's one more version of Newton's second law, and here, look, there's a little room right in here. I can squeeze it in. A little bit of room, and it goes like this. The sum of the moments about A is equal to IG alpha plus R cross MAG. That's what we're going to do to check our work. And if all that works, of course we know we got the right answers, but what if you didn't have an answer book? Well, we can check our own stuff. We don't need no stinking answer book. Okay, let's do it. Sum of the moments about A. Well, there's only one force that gives you a moment about A, and that's this P. I don't know if you like the way I did that. You might prefer writing the component going horizontally. Here's another way of writing that. Take P, which we think is 7636, times the cosine of 30. You understand that's this component that's pushing to the right. And multiply it by 1.5 feet. And you're done with the left-hand side. That's the only moment about point A acting on the wheel. Okay, now on the right, we have IG of alpha. Now where's IG? I got lost there. There it is. It's, I might need to make some room here and squeeze this in. It's 1.74689 times alpha, which is 18.93. 18.93. That's IG alpha. But we're not done yet. We have to go plus R, which is 1.5 feet, times the mass, which is 50 divided by 32.2, times the acceleration, which is, did we ever get it? Yeah, 28.4. 28.4. All right, now here's our check. Let me look at this equation here. It's pretty long and ugly looking. Okay. Now we're going to plug in our numbers and see what happens. 0.25 times 76 blah blah. Let me do that. 0.25 times 76.36 times the cosine of 30 times 1.5. Okay. I need the room here. All of this stuff on the left is equal to 24.79. Let's just round it off to 24.8. 24.8 foot-pounds. That's what you've got. That's the moment about A. It's 24.8 foot-pounds. Now we're going to see if we add all this up, if we get 24.8. Well, here goes. I'm going to take 1.74689 times 18.93. 18.93. Plus 1.5 times 50 divided by 32.2 times 28.4. Well, I did that, and I didn't get 24.8. Something bad happened. Let me do this again. Maybe I goofed up. That's the moment about G. And there's your alpha. Okay. And there's R.
I think you times friction on the left.
So we figured out what the truth of survival was, and then we arrived.
You multiplied friction in there.
I don't want that. I don't want that, do I?
I know what it is.
Oh, I appreciate that so much. I think I need to not add that friction in there. Yeah. Okay, now do I have it right now? Now let me see. Yeah, let me try it again. Who was that? Who did I just talk
Shane.
to? Say again?
Shane.
Shane. Honk and thank you point right there for Shane. All right. I don't want to multiply by that. I want to do this. Let me try that again now. 76.36 times the cosine of 30 times 1.5. I'm getting 99.2 foot-pounds. 99.2 foot-pounds clockwise is what the moment is about A. Now I'm going to add all this stuff up. 1.74689 times 18.93 plus 1.5 times 50 divided by 32.2 times 28.4. Boy, Jove, I'm getting 99.2 foot-pounds. Well, technically, it's not foot-pounds. It's that's feet. Now let me think about this. The 1.5 is feet, and the 50 over 32.2, that's slugs. And the 28.4, you know what that is? That's feet per second squared, isn't it? Yeah, it's feet per second squared. So technically what we have here is 99.2 slug. Running out of room here is my problem. Slug feet squared per second squared. But you know what? That's equal to a foot-pound. It's the same thing as a foot-pound. Yay! We checked it. All of Newton's 4 laws apply, and they're all good. Okay, well, do we have any comments or questions about this? Was very hard, wasn't it? This was very difficult. And being lazy, I put it into a 3x3 simultaneous thing in my calculator. And I bet you all have those calculators. Well, we have 5 minutes left, and I want to talk to you about the next chapter. Now, it's not on your test, but that's where we're going to be when we gather on Monday at 9:30. But unless you have a comment or question, I'm going to erase all this wonderful stuff. I hate to, it's just so beautiful, isn't it? You love this stuff, don't you? Okay, well, I'm going to erase it. Nobody said anything, but I'm proud of you. Thank you, the ones that helped us wade through all this. It wasn't easy. Did I ever tell you that this course that you're taking right now is the hardest engineering science course? I think it's harder than thermal, personally. I think it's harder than strength of materials. It's harder than statics. All right, we got 5 minutes, and I want to talk to you about chapter 18. It's not on your test, and it deals with kinetic energy. Only the book uses a symbol T for kinetic energy. And here's their equation for kinetic energy. Well, now wait a minute. That's the equation for kinetic energy of rotation. There's also the kinetic energy of translation. And that we know and love that equation. We've known that for a long time, 1/2 mv². Now, if you want the total kinetic energy of a body. If you want the total, well, then what you have is you take the kinetic energy of translation and you add the kinetic energy of rotation. Does that make sense? You'd add them up and you'll get the total. Now let's do an example. We got time. We got 3.5 minutes. Let's suppose we take, let's do metric system. Metric is so much easier. Suppose you take a disc, a 200 kilogram disc with a radius of, we'll just say it's 0.05 meters. So the moment of inertia for that disk is 1/2 the mass times the radius squared, if you have a disk. You know, a disk is sort of a deal like that, kind of like a coin maybe, huh? Like a silver dollar maybe, or a quarter or whatever. Well, let me do that and see what I get. I got 0.25. Do you suppose I might have done that right? Now let me double check it. Boy, Jove, I think that's right. And let's suppose it's rolling on a surface. And we'll just make something up. So, suppose it has an angular velocity of 2 radians per second. Well, we could get the kinetic energy of rotation. I tell you what it'd be. It'd be 1/2 the 0.25 kilogram meter squared times 2 squared. That would be the kinetic energy of rotation. Oh, gee, I'm running out of time. But see, it's also got a kinetic energy of translation because the velocity would equal 0.05 omega. And so the velocity is 0.05 times 2. I could have done that in my head. The velocity is 0.1 meters per second. So the kinetic energy of translation is 1/2 the mass, which is 200 kilogram, times 0.1 meters per second squared. Now, if you add that kinetic energy of translation to the kinetic energy of rotation, you get the total kinetic energy. It's sad, but our time together has come to an end. I hope you enjoyed it. Do you have any last comments before I push this ugly red button here? Here's your chance to speak up, and we'll study this next week when we meet at 9:30 on Monday. Any last? Yeah, go ahead.
Exam 3 isn't showing up on my Blackboard.
I'll contact my IT person right away.
All right, good.
Yeah, it should show up. You got till what, Saturday night, and I'll make sure it shows up. Anybody else? Thank you for mentioning. Who was that?
This is Braxton.
Braxton, thank you for speaking up, Braxton. We'll make sure it's on there. Anybody else?
When do you usually post up your videos for the week?
They'll be posted by the weekend for sure.
Okay.
I'll just, my IT person's pretty busy. She's got a full-time job, but she'll post them. We'll get them up.
Okay, thank you.
Yep. Anybody else? Okay, well, that was fun. We'll take care of that, posting that test for you. Ta-ta, students. See you next time.
Bye.
Bye-bye.
Paragraph 34, G carded, please.